Hey everyone. The notion of independence is the central concept of probability theory. We defined independence formally in the last episode, and for the rest of this season, we will practice with it. We'll solve a lot of problems about independence. Let's recap definition of independence. Events E and F are called independent, and we denote this using this symbol that resembles orthogonality if the probability of their intersection equals the product of their probabilities. Notice how this definition is symmetric. If you flip E and F, the intersection remains the same and the right-hand side obviously remains the same. So E is independent of F if and only if F is independent of E. This is in stark contrast to the notion of conditional probability, which was not symmetric. P of E conditioned on F is not the same as P of F conditioned on E. The correct way of flipping the order of conditional probability was given by Bayes' formula. Back to independence. This definition applies to two events. What if we have more than two? If we have any number of events, they're independent if a similar formula holds for any combination, any subset of those events. For instance, the probability of E2 intersection E7 intersection E9 is the product. And another example, probability of E1 intersection E3 intersection E6 intersection E8 is also the product. And so on. All of these equations must hold for these events to be independent. More compactly, we wrote it as the requirement that the probability of the intersection of any subset of the events EI is the product of the probabilities of EI for any subset I, such as the subset 2, 7, 9, or 1, 3, 6, 8, and so on. We also noticed in the last episode how independence is stable with respect to set operations. Stability means that if the events are independent, then any events formed of them are also independent. For instance, if we have events E, F, G, and H that are independent, then the events E, F complement, and G union H are also independent. We're allowed to apply any set operations, complement, union, intersection, or any combination of them, and the events will still be independent as long as they involve different events. And now let's have fun with problems. Today we will revisit our very first problem of this series, which is the birthmate problem. How many strangers do you need to ask to get a 50-50 chance to find someone with the same birthday as yours? What's your feeling about this? Would you need to ask 10 people maybe to meet your birthmate? Well, maybe you need to ask 100 people, or maybe 1,000 people. There are 365 days in the year. So my feeling is that it's going to be in the hundreds. If you ask 365 people, then maybe there is a reasonable chance that some of them will be with the same birthday as yours. Let's find out. Let's denote this number by n and find it. We need to find someone with the same birthday as yours. Let's denote this event by E. What does E really mean? Among all those strangers, either the first one is your birthmate, or the second one, or the third one, and so on and so forth. It's a logical operation or corresponds to the union. So we can express our event E as a union of the events EI, where EI is the event that the ith stranger has the same birthday as yours. Are these events mutually exclusive? Think about it. No. It could very well be that, let's say, the 5th stranger you ask and the 10th stranger you ask are both your birth mates. You all three share the same birthday. So these events are not mutually exclusive. What do we know about them? The events EI are independent. And that's because we assume that we ask independent strangers. What else do we know about these events? What's their probabilities? What's the probability that a given stranger is your birth mate? There are 365 days in the year, and only one of them is your birthday. So the probability that the stranger hits exactly one out of 365 days is this, 1 over d, where d is 365. So our event E of interest is a union of independent events, and we know their probabilities. How can we compute the probability of the union? Inclusion-exclusion principle is one of the ways to do that. But the formula of inclusion-exclusion principle is complicated. It has a lot of sums, and each sum is complicated. What's the easier way to do that? A simpler way is to pass to the complement. By De Morgan's law, the complement will turn the union into intersection. And the probability of the intersection can be found easily because the events are independent. So this is our plan. Let's do it. We pass to the complement. By De Morgan's law, the complement of the union is the intersection of the complements. The events EI are independent. Therefore, their complements are independent too. This follows from the stability property. Now we use the definition of independence. The probability of the intersection equals the product of probabilities. The probability of each event is 1 over d. Therefore, the probability of its complement is 1 minus 1 over d. And when we take the product of n such terms, we get this. Let's simplify this expression a little bit. You may notice how this is similar to the classical limit 1 minus 1 over d to the d, if d is very large, becomes closer and closer to 1 over e, Euler's constant. And that's because the limit of x over d to the d is e to the x. And now we apply this for x equals minus 1. So what's the difference between this and this? The exponent is different. We have the exponent n, and here the exponent is d. Let's make the exponent d and correct it, raising it to the power n over d. If d is very large, according to this limit, this expression is close to 1 over e. And remember, d is large. D is just a number of days, 365. So the probability we're computing is approximately 1 over e raised to the power n over d. Or in other words, e to the minus n over d. We would like to have a 50-50 chance to find someone with the same birthday as yours. In other words, we would like the probability of E to be equal to 1/2. The probability of E complement in this case would also need to be equal to 1/2. So we would like this to be equal to 1/2. And we're trying to find how many strangers we need to ask. We need to find the value of n. Solve this equation in n. Take the logarithms of both sides multiplied by d, and you get that n will be d times natural log 2. D is 365, And putting this in the calculator, we get approximately 253. And that's the answer. In order to have a 50-50 chance to meet your birthmate, you need to ask around 253 strangers. This solution was approximate, so the probability is not exactly 50-50, but it is 50.05 to 49.95 chance. Check it using the exact computation. Thank you, and see you for the next episode for the next problem on independence. Have fun.